Hey, put your pencils down, look up. Oh, take one, pass it down. Put your pencils down, look up. We've been looking at electricity and magnetism. Together, they're called electromagnetism.
Electromagnetism for babies. This is a ball. This ball has positive charge. This charge creates an electric field. Positive charges move with the field. Positive charges repel other positive charges. This ball has negative charge. This charge creates an electric field in the opposite direction. Negative charges move against the field. Negative charges attract positive charges. Negative charges repel other negative charges. Positive charges attract negative charges. Field lines flow from positive to negative. Positive and negative charges follow them. This is a magnet. It has a north pole and a south pole. It creates a magnetic field. Other magnets want to line up with it to look like this. Magnetic fields cause positive charges to circle counterclockwise. Negative charges circle clockwise. Magnetism affects charge, but charge also affects magnetism. Negative charges moving together create an electric current. The current creates a new magnetic field. Now you know electromagnetism.
Cute, but also pretty accurate. Let's jump on in. Lenz's law. So this is going to be an English law, and it's going to explain when you're inducing a current in a coil by changing the flux, what direction will the current in the coil flow? Consider the following situation. So it looks like we're moving a north pole towards a coil of wires. Ella's going to get off her phone. Okay, thank you. First question, will there be an induced current in the coil? Well, we're talking about a coil, not a wire. So the equation for the induced current in a coil was well, this was the equation for a voltage, but since the coil has resistance, there'll be a current. It was negative N change in flux over change in time. And really the key is right there. Is there a change in flux? As I move this magnet in this direction, will the number of magnetic field lines going through this area change? Yes. It's basically as though you're making the magnet stronger. You can make the magnet stronger, the magnetic field stronger in several ways, bumping up the actual magnetic field, or move the magnet closer. That's just the same as making the magnetic field stronger. So there will be an induced current. The real question is, what direction? Okay? Don't write this down. Here's our thought experiment. One possibility would be that we create an induced current with a north pole right here and a south pole right here. One possibility. But what would happen between this north pole and that south pole? Are they like or unlike? So unlike poles attract or repel, which would pull this even faster, which would change the flux even faster, which would make this magnetic field even bigger, which would make your induced current even larger, which would pull this in even faster, which would make this magnetic field even bigger, which would make your current even larger. You know what? That violates the law of conservation of energy. That would be, if that was the direction, that would be free energy. And so the universe steps in and says, nuh-uh. This is what Lenz's law says. An induced current will always create a magnetic field that opposes, everybody underline the word opposes, the magnetic field, the change in flux that caused the current in the first place. In other words, up here, I have a north pole moving to the right. What would resist a north pole moving to the right? Another north pole pointing to the left. That's the direction of the current, which means now I can hold the solenoid in my thumb in my hand, point my thumb north, and you know what, Eric? The current is going to flow this way. We're going to practice this a whole bunch, but this is the universe stepping in and saying, no, you don't get free energy. I'm always going to create a magnetic field that opposes what you're trying to do. And in fact, that's why when you spin a coil, you feel a force resisting you. It's creating a magnetic field opposing the one that you're using to create the current in the first place. In other words, you get nothing for free, ever. Except maybe your mother's love. Maybe. This explains the negative in Faraday's law. Faraday's law, with the negative, it tells us that the induced EMF, the induced voltage, it's going to be created by a current that's creating a magnetic field opposing the magnetic field that created the current in the first place. Let's look at a few. Example 1. A loop is placed in a region of magnetic field that is into the page. The field then changes direction so that it's pointing out of the page. What's the direction of the induced current? Well, there's two possibilities. It can either be going this way or it can be going that way. Here's what we do. Look at the final picture. What direction is the magnetic field in the final picture? What would resist a magnetic field pointing out of the page? Another magnetic field pointing into the page, because like poles repel. So everybody point your right thumbs into the page. Will the current that's induced be clockwise or counterclockwise? You know what? It's going to be going this way, yes? If it was the other way, suddenly it would be contributing to the magnetic field, and you just have this violating conservation of energy loop. To describe this, we'll use as our abbrev for clockwise. Our abbrev for counterclockwise, it's going to vary depending on where I stole the diagram. It'll either be CCW for counterclockwise, or if I stole it from a British website, it'll be ACW for anticlockwise. The diagram below shows an aluminum ring and the current induced in it by the nearby magnet that is free to move along its central axis. The magnet must be A, stationary. Can't be stationary because that wouldn't give you a changing flux. That would not induce a current. Moving to the left, moving to the right, spinning. It's not spinning. So in the ring, that's the induced current. Hold the ring in your hand. Curl your fingers in the direction of the induced current. In that ring, Aiden, what side is north? Left side or right side? This is from the ring, a north pole there, a south pole there. So here's the question. That must have been created to oppose whatever we're doing. Would moving a south pole towards the north, or would moving a south pole away from the north be more difficult? Which one are you going to feel something resisting you? It must be moving to the right. You must have been moving a south pole away from that ring. Said the ring. I'm going to tug you back because you get nothing for free. That's Lenz's law. We're going to practice this a bunch. What will be the induced current in the circuit below flowing through the 15 ohm resistor, and will it flow from X to Y, or will the induced current flow from X to Y or Y to X? They didn't give me enough information to solve this. Okay, look at the final picture. What direction is the magnetic field in the final picture? Out of the page. What will resist a magnetic field pointing out of the page, Taya? A magnetic field pointing into the page. So the induced current in that coil will create a magnetic field into the page. Everybody point your right thumbs into the page. I think if you do that Taya, you find the current in the coil is going to go that way. That's the induced current. And now just follow it, follow it, follow it, follow it. You know what? From Y to X. Yes? From Y to X. Oh, and if you gave me more information, I could solve. If you told me the strength of the magnetic field and how long it took, I could actually calculate. Oh, and how many coils of wire there were. This looks like a single coil of wires, but if there was more, I could solve it. Example 4. If we're moving the magnet to the left, find the coil's induced north pole and the direction of the induced current. So what pole, Joanna, is closest to the coil, the south or the north? Focus on that one. Is it moving towards the coil or away from the coil? Whatever magnetic field the coil generates will resist that. What would resist a north pole moving away? Yeah, it's going to put a south pole right there saying, come back. North pole there. Now hold the solenoid in your hand. Use your right hand solenoid rule. Is the current curling upwards from the bottom, or is the current curling downwards from the top? This way, yes? Current is going this way. Is that okay for you? Mr. Dueck will now show you a nice demonstration. Yeah, this is pretty cool. Pause the video for a second. See what Nicole was seeing. I have larger versions. So this is a copper plate. This is a very strong magnet. We're going to drop it and watch what you'll see. That's Lenz's law. It created an induced current in that disc on the bottom, resisting, I don't know whether it was a north pole or a south pole moving down, but you saw it suddenly come to a stop. This allows you to have a braking system with no moving parts, which, oh, that's kind of handy. I believe there are a few roller coasters that use this as part of their braking system to slow it down. I don't remember which ones. Video, magnet in copper pipe. So this one I like because it's got a bigger diameter. There you go. There's Lenz's law. You can see it's clearly not in free fall. There's another force acting on it. And in fact, if you're really, really, oh yeah, you can even do it this way too. You're inducing currents in the side that are resisting whatever magnetic field you're moving towards it. Pause the video for a second. In fact, if you're really quick, you can just keep inverting this and you can keep it locked in there the whole time, like that. That setup is about 500 bucks. I'm sorry, I'm not paying for that. I'm too cheap to do that. Those big magnets, Eric, are crazy expensive. Okay. Then I have Lenz's law with copper pipe. Oh, this is good old MIT. Oh, by the way, I got even better stuff to show you. Neater examples of Lenz's law. But so an iron ball that's not magnetic, drop it in. Okay, free fall. Same old, same old. Time was about 0.02 seconds. Spherical magnet, same size. Yeah, they make spherical magnets too. That's what you saw as well, as it was slowly making its way down. It's inducing currents above and below. You're not going to get a shock. It's not doing that big, but yeah. So how does it work? The falling magnet induces a current within the tube. By Lenz's law, the current creates a magnetic field that opposes the field that's creating it in the first place. That's the direction of the induced current. Back to notes. Says determine the direction of the induced current in the loop or the coil in the following diagrams. Okay, we're going from no magnetic field to, oh, Ella, what direction is this magnetic field? So our final magnetic field is which direction? Say it again. What would resist a magnetic field pointing into the page? A magnetic field pointing the final current will point out of the page. So what will that be? You'll point, I guess if you're holding the solenoid or doing the quote, you know what, point your thumb out of the page. I think the current here would end up moving in that direction, or CC, no, counterclockwise. Is that right? I think. What about if we started into the page and ended up with nothing? Well, really what we're doing is we're making into the page weaker. What would resist into the page weaker, making into the page, what's the opposite of weaker? Stronger. Now you're going to get a strong, doing it in reverse. As it exits this field, it's going to induce a magnetic field. Oh, you're trying to make into the page weaker by removing me from that magnetic field? I'm going to make into the page stronger. Into the page stronger would be point your right thumb in. Did I do this one backwards? No, out of the page, into the page this way. Yep. It would make into the page stronger. Compare that with this diagram. We're going from nothing to out of the page. Our final magnetic field is out of the page. What would make out of the page strong? Sorry, what would resist out of the page? So point your thumb into the page. It's going to create a magnetic. It's going to create a current in that direction. Here, we're starting with a magnetic field out of the page, and we're removing it. You can think of that as saying you're making out of the page weaker. What would make out of the, what would resist out of the page weaker? Making out of the page. So out of the page stronger. You know what? It's going to be in this direction. Ooh, Ashley, what pole is closest to the solenoid, north or south? So if we zoom in on the one that's closest, we have a south pole getting stronger. What would resist a south pole getting stronger? A north pole would resist a south pole? Ah, see, by the way, if it was this, then suddenly it would move even faster and you would get a bigger field which would move even faster. That's free energy. Lenz's law says, yeah, no, you don't. It's going to put a south pole there, a north pole there, and now I can hold that in my hand. I think the current is going to flow that way, I think. Is that right? Let me know if I'm making a mistake, but I think I'm good. Moving a south pole away from the solenoid. So, Victor, what would resist a south pole getting weaker? It's going to put a north pole right there and say, no, you don't. South pole there. And so now, just thumb there. You know what? The current is going to be curling upwards, and then it's going to come down, and the current's going to go that way. Getting the hang of this okay, Jaya? Yeah. Okay, I'll let you try the other two on your own, but again, some nice applications here. There's a nice little magic trick that you can set up with a guillotine.
This is my guillotine. It's got a copper blade on it. It's about 4 or 5 millimeters thick, and it weighs, as you can see, on the order of 30 newtons.
I love the fact that he gave the weight in newtons. Thank you, David Willey, one of my nerd heroes, for giving weight in its proper units. Newtons, not kilograms.
Maybe a little more.
So about 3 kilograms of mass.
Yeah. It's in these aluminum cans. I put it up here. Let me show you what it can cut. This is actually much better done with a cantaloupe or watermelon, some fruit little.
I saw him do this on the Jay Leno Tonight Show to Jay Leno with a watermelon. This is really nice.
Let me show you what to do. Soda can. This slice it. It'll go pretty much through. Here we can see that can got totally crushed there. And
So
actually chopped.
let's put our bare foot in there. This, except I can. These are four really strong magnets. Now, magnets are not attracted to copper, okay, nor aluminum, so there's no sticking to these pieces of metal. Iron, like this little piece of chain, oh yeah, get to that and make some force work. With the blade, not so much. Now, here, so that the blade isn't going to get some on the right hand. It slides past them. Gap of 2 or 3 millimeters. But now it's safe for me to put my moving through there. And I can't reach with my arm and pull this in, but let me put my foot in there for you. Okay? And just to show you that I'm not cheating, let's take the shoe off and drop this onto my foot. Why didn't it chop through my foot? Electromagnetic induction. It's science, guys. That's what's going to be. Lenz's law. Lenz's law. And in fact, you can set up the best barbecue ever.
Let's switch it on. Let's see what it does. Through this coil of thick wire, we're about to pass a huge alternating electric current. On top is a 1 kilogram aluminium plate. So we hear this noise. What's that noise?
It's the vibration of the plate because it's vibrating at the frequency of the set of this one.
Whoa! Whoa! How does it do that? To find out, I've come to the place where it all started, the Royal Institution in London. This is the key to Faraday's magnetic lab.
This is as close as you get in science to holy ground. This is Michael Faraday's actual lab. They've kept it intact.
Block somewhere. From the 1870s also became a storeroom, which is why it survived, and it survived intact, all the joinery, giant electromagnet, exactly the same as Faraday.
So this is exactly as Faraday would have had.
That's right, yeah.
In Faraday's time, it was known that electric current creates a magnetic field, but it remained an open question whether the reverse is possible, if a magnetic field could generate electric current. Faraday answered this question with his most famous apparatus.
Faraday's electromagnetic induction ring, which is this.
In August 1831, Faraday wrapped 2 coils of insulated wire around this iron ring.
But in 1831, you could not go down to your local electric hardware shop and ask for some meters of insulated wire. You had to insulate the wire as you went, and so as you pushed and pulled the wire out of the ring, you had to insulate it. It takes 10 working days, which is a huge investment of time.
But the investment paid off. When Faraday connected a battery to one of the coils, he saw a brief pulse of current in the other coil. And when he disconnected the battery, he saw a pulse of current in the other direction. He realized that current was induced in the second coil only when the magnetic field through it was changing. And if they hadn't been wrapped on the same ring, Faraday may have noticed that the 2 coils repel each other when the current is induced, and that's due to the interaction of their magnetic fields.
Lenz's law.
Which brings us back to this. Through the bottom coil, we are passing a huge electric current, 800 amps, which alternates in direction 900 times per second. This ensures there will always be a changing magnetic field above the coil. Instead of a second coil, we're using the aluminium plate, but the principle is the same. The changing magnetic field induces currents in the plate that create an opposing magnetic field, so it levitates. How awesome is that? This current is not only good for levitating the plate, it can also make light bulbs glow.
Okay.
Oh, thank you. Oh!
That is cool.
Not too close because it's will burn the arms.
Can I put it there?
Yeah.
And just as current in a toaster element heats it up, the induced current in the plate dissipates its energy as heat.
Thank you.
Yeah, to see the temperature.
Check out how hot this plate is.
That would be the best dinner centerpiece ever. It floats, it magically makes it light up, and you can grill on it, baby. Come on! Oh, I want. All you need is 800 amps and 900. That couldn't be that hard to. Well, how many amps you get out of your power outlet? 15. 800. That's a huge amount of current. Okay.
Oh, that is nuts. Is this your favorite demo?
It's like a fun barbecue.
Tell me this is not the best dinner table centerpiece. It levitates, it gives you light, and you can cook on it. And all the while, you're demonstrating Faraday's law of electromagnetic induction.
Okay, that's pretty cool. What's your homework? So, number one, and the answers are just in brackets. In other words, the answer to 1A, you should find the current is clockwise. Clockwise, I stole this from a British website. C, it should be anti-clockwise when you use Lenz's law. So always ask what magnetic field would resist the final situation. That's what's going to generate. Number one is good. 2 is good. 3 is good. 4 is good. 5 is good. 6, 7. You'll have time to work on this on Monday as well. Yeah, 8 is good. We'll pause there.